Lab 4, Oscillations. The purpose of this lab is to investigate the motion of a spring mass system, with the mass swinging in an arc while oscillating. I will be using Tracker to analyze the experimental motion, and I will be using GlowScript to create a computational model to predict the mass's motion and energy changes. I will also be using GlowScript to compare the motion of the experiment and model. For this investigation, I will be making use of Newton's second law and energy principles. Preview the results. The total change in energy of the system is zero, meaning the energy principle holds up. Physics principles. Newton's second law says that the rate of change in momentum of the system is proportional to the net force acting on the system, where F naught is equals to the P dt. F naught here is specifically equal to the addition of spring force and the gravitational force, where F net is equals to Fs plus Fg. The energy principle states that the change in the energy of a system is the sum of the work done by the surroundings plus the thermal energy exchange with the surroundings, where the change in energy of the system is equals to work done by surroundings plus change in energy, thermal energy exchange with the surroundings as shown. For this investigation, the system is equals to the ball, spring, and earth, while the surroundings is equals to nothing. Because there is no exchange of thermal energy and no work done by the surroundings, the change in ESIS is equals to zero. Therefore, the changes in the energies within the system, kinetic energy, gravitational energy, and spring energy added together equates to zero, as shown. Here is the data collected from the sample video provided in the lab, and here are the results collected from that sample video using Tracker. The initial position is minus 0.119 in the x component, minus 0.637 in the y component, and 0 in the z component meters, and the initial velocity is 0, 0, 0 in all components meters per second. The object's mass is 0.402 kg, and the magnitude of L is 0.7 meters. I calculated L naught and K using the analysis of the oscillations up and down of the spring system, as they gave a more accurate representation of the values. I used the equation K is equals to 4 pi squared times M over T squared to find K, and also used the equation mg is equals to ks. To find t, I used the time it took for the 3 intervals and divided it by 3 to get the average t. Using these two equations, I found that k is equals to 6.83 newtons per meters, and L naught is equals to 0.123 meters. I also put the data from the observed motion into a CSV file for later use. For the code, I inputted the initial conditions and the values we calculated previously. I also added the equations to define the length of the spring and define the energy equations using the formulas for each corresponding energy. Added together, they give E, which is the total energy. In the for loop, I defined the initial energies as their corresponding energies, and I also defined the forces, gravitational force, and spring force acting on the system. I added these forces together to find the net force. I also defined the velocity and position update formula to account for every iteration. I redefined the equations for the spring length and spring direction within the loop. I also calculated the change in the energy for all the energies defined in this computational model using the final minus initial energies. So here are the results of my computational modeling from GlowScript. And I put the file, the CSV file in, and as you can see, the results are as shown. So as can be seen in the previous video, the spring systems are oscillating, with the blue ball representing the computational spring system and the red ball representing the observations of the experiment. The graphs can also be seen displaying the change in the energies over time and the positions in both the x and y axis over time. So the discussion for the model versus the experiment. As you can see, in the graphs of position over time are similar at first for the model and experiment, but starts to deviate as time goes on, which could be explained by the fact that minimal amounts of energies would be escaping the system, because in reality, in the experiment, the system is not isolated from the surroundings. What if and what does it mean? Is the energy principle satisfied? Yes, it is. In our model, we stated that there will be no external forces or work done acting on the system, so change in ESIS is equals to 0. In the model, we also obtained a graph, and while we can see different energies on the graph, the change is that all of these energies add up to 0, as shown with the yellow line representing the change in total energy that lies on the x-axis. Comparing the time periods, choosing different axes to calculate from produces deviations in the period, as is shown on the right, with the equations for the calculating with the x-axis and calculating with the y-axis, which leads to different spring constants that would affect the graphs produced differently, and the results would also affect the results produced. Sources of error. Some sources of error may include not properly placing the trackers in the tracker at the center of the mass attached to the spring, and another source of error is that the system is not actually a closed system, so other forces may be acting on the real spring system. Thank you.